I think it is started. So let's start with a brief intro. So who am I? I'm actually not this guy. This guy. So I'm a coordinator for Project Falcon, and I work at eBayBigdataMeetup where I work as a lead. I've been associated with the Project Falcon since its incubation days. So what is Apache Falcon? So Falcon is a data processing and management solution for Hadoop, which is designed for data motion, coordination of data pipelines, lifecycle management, and data discovery. I'll explain all these fancy terms as we go along. So what is Falcon offer? So basically Falcon offer these core services. Lineage, process release, data management, retention, replication, acquisition, SLA, operability, and all these services on your data on Hadoop. And to understand how these services are useful, let's look at the typical life cycle of data in Hadoop cluster. So you start with the data being acquired or imported. So you will have typically your relational database where you will have your dimensional data. For example, let's say there's some e-commerce company, and in that they will have their catalog of the IDs and the home names, etc., and all those things. So you will import that data to look up for your reports, and then you will processing on that data. And you won't be keeping your data in the HDFS forever, so you will need deletion or retention of the data. And after some time for business continuity purposes, etc., you will also need to archive some of your data. And for the same reason of business continuity and other reasons, like you will also want sometimes for some of your data to be replicated. And then in the end, you would like your data to be exported back to relational databases where other end users can consume them and play them in various formats and reports and all those things. So this is the typical life cycle of a data. And this is how typical data pipeline will look like. So you will have these nodes in this graph will show various processes. So you will have your data which will be consumed, the raw data will be consumed by the first process, and it will clean up the data purely and then pass it on to the new consumers. The same data can be consumed by multiple processes. So typically, once produced one will be consumed by the next ones and so on so forth, and then the last one will be producing data in the format which will be consumed by the end users. So coming back to what services Falcon provides. So data retention is a service which Falcon provides. So what do we mean by data retention? Data retention is basically you have a lot of data in your cluster. You imported like let's say your metadata and some raw data, etc. And different data will need to be retained in your cluster for different durations. For example, my raw data will be needed to be retained, for example, let's say 3 months. For audit purposes and all those things. Whereas some of the reports which we generate, they might be needed for like a shorter duration that I put them in the database. So I need them in HDFS only for let's say 1 week. So different data will need to be in HDFS for different time periods. And after that, you will want them to be predicted. And there can be several ways in which you want the data to be predicted. For some of your data, you can say, hey, I want this data to be encrypted as soon as it has more than 5 instances of this data. So as soon as you have more than 5 reports, delete the other ones. Or you can say, hey, I want the data to be deleted which is not being used for the last 7 days, but at the store data I want that to be deleted. Similarly, you can say on the creation time, hey, whatever data was created 1 month before, all that data should be deleted. So all these are part of data retention service which Falcon provides. You can declaratively declare what kind of policy for retention you want, and Falcon will do it for you. Similarly, you have lake data management. So in typical pipeline, what we will have is there will be issues, and sometimes what will happen is some data will come late, or some data will be corrupted, and they will need to rerun your pipeline. There are challenges associated with it because, let's say, your raw data was wrong or somewhere in between your pipeline the data was wrong. You don't need to run only just one process. You need to actually run all the subsequent consumers as well. So if I go back, yeah, this data taking. So let's say one of those networks was to be rerun. Let's say there was some processing mistake that we did. Then we want that all the subsequent consumers of that process, they should also automatically rerun. And Fathom provides this as a service when we say the lake data management. So only we can be clear that, okay, I want this lake data policy. Whenever the data comes in, it should automatically rerun using these workflows. So Falcon takes care of your data management for you in that sense. Similarly, data application as a service. So when we say, let's say that there is several use cases, for example, for business related purposes, you might want to keep replicating some of your data into two clusters. If one cluster goes down, the other cluster can automatically come up and take load. The other use case, which for example, what we have in Hadoop is you can have various data centers. We have various data centers in various zones, like we have one in London, one in US, in Japan, etc. So in those data centers, we do some sort of integration. We don't transfer all the data. We do some sort of integration, and whatever reports are generated, we send only those reports. So those reports, aggregated reports, summary reports we call them, those are replicated to the main global cluster, and there they are aggregated and processed further. So that's another use case when you want data replication. And replication again has certain use cases. For example, if you want to specify that these are my critical processes, I want them to be replicated faster, and others to be taken less priority. I want to specify this is a bandwidth and maps, etc., that these processes can use. And all of these concepts you can specify using Apache Falcon, and Falcon will do the replication for you using the declarations which you are specifying. Similarly, data acquisition, the import and export. So as I said initially, there is relational database typically, where you will have your metadata or dimensional data as it's called sometimes. So you will want to import that in your HDFS, maybe through Spoon and all those tools. So you can use Falcon to do those import. And similarly, when you have your last process in the pipeline as generated reports, you can use export functionality to put that data back into this relational databases or other data warehouse you might have for reporting purposes. So why we need Apache Falcon? So some of you might be using Uzi, which is a workflow engine, and you might be asking questions. So some of these things I can do them through Uzi. So why do we need Apache Falcon? There are lots of reasons that for the functionality which we have mentioned is an overlap with Uzi. So I will clarify why we need Apache Falcon. So there are several reasons. The first is Falcon is a holistic declaration of the intent. So what that means is you can establish metadata and relationships between various processes through the data. What that means is, let's say process E consumes data, which is T1, let's say, and then it consumes T2, which is consumed by process B and process C. And in Uzi, you can declare different data sets, so you want to be able to see that relationship that the same data is consumed by B and C. So Falcon takes out that abstraction and says that this data is called a feed, and this feed is being consumed by process B and process C. So that kind of neat abstraction is what Falcon provides. Similarly, if you use Uzi, then you will have to specify there is Uzi coordinator which you can use, and in that you can specify each data sets the path and the path and the frequency, and then you use. But let's say this same data is being used by, let's say, several processes, and tomorrow the data changes its location. You want to move that, you are doing customization or something, then you have to make change in all those processes. So Falcon takes out that and creates an abstraction which is called feed and takes care of all those problems for you. The third advantage which Falcon provides for you is a single concept calculated views of the entire life cycle of the data. So my data is being imported to this relational database, and this is consumed by these processes, and this is maintained for 30 days, and these are the access control lists of this data. All that information is available to you in a single page, and that's neat view is what Hadoop provides. There are far more capabilities and features which Hadoop provides. I discussed them as we go along. Another thing is automated dashboard. So typically you will have in your data center you will have lots of pipelines. There is one pipeline A, one pipeline B. They will start from some point early or not, and then they will go on. And you want to see, typically you want to see your health of the pipeline, because in the end, the pipeline generates some meaningful reports, and you want to see how is the pipeline doing. You can data generated online. So pipeline provides you the pipeline dashboard, where you can see that okay, these pipelines are clean, they are really fine, and they are meeting their SLAs. And there are these pipelines which are not fine, so you can take care of those. Yeah, ways to do that, I will discuss that as we go along. But this single view of all your pipelines is what Falcon provides. So let's go to an overview of Apache Falcon. So Falcon has basically three entities. One is cluster, one is process, and the last one is feed. So the process depends on feed. Process will either take feed as an input, and it will generate feed as an output. It's optional. You can optionally take an input, and you can optionally generate an output feed. And process is executed on a cluster. A cluster is basically configuration of various endpoints, which can specify, for example, your extent of registry, for example, your etc. So all these configurations, etc., are stored in one place. Your HTTP and private endpoints. They are stored and they are provided as that abstraction to the process and the feeds. Feeds also depend on cluster, because on that cluster they have their location, which is the data which I am available in this cluster, in this location, and these retention, etc., all those jobs which are scheduled, they will be scheduled on those cluster endpoints. I'll show you a detailed view of those. I'm sorry, this is not really visible. But this is the DSL which Falcon uses. In this, we specify a cluster specification in this XML. And you will see that there is a memory interface endpoint which is used by this for replication. And when we provide replication as a service, that is used by this endpoint is used by feeding end processes. Then there is a write endpoint cluster, which is for writing data to HDFS. It's required for that use case. And then there is a MI endpoint. Then there is a workflow endpoint. By default, it's using, but you can have your choose your workflow region and provide that endpoint. Then there is a live data store to register actions and data availability events. And in the end, there is a messaging endpoint which is used for sending alerts of data being available or some workflow, jobs to exchange, etc. And the last couple of lines for SQL directories which are used by Falcon internally. These are temporary working and staging directories which Falcon uses. Similarly, there is a feed specification. So in the feed, there is a frequency matrix. What is the frequency of the data availability in this feed? And then there are some configurations for XML. You can specify if after this close time, let's say in this case it says if 2 hours after its instance time, it's not already the same error. Then there is retention, which you have declared specified that I want this data to be retained in this cluster for 2 days, and you can specify this per cluster. This period is running on 2 clusters per secondary, and you can see that retention is specified per cluster. You can change that. Maybe on one cluster you want less retention, and on the other cluster you want higher retention. The other Both these processes are actually subject to replication. The time parameter is time is equal to source and time is equal to target. This specifies that for the source you have to replicate your data to the target, and that schedules the replication for you automatically. You can have multiple sources and multiple targets. Then this is the location of the data. So you just at this location, the data will be available. And so in the end, there are ACS functions for this field. Similarly, we have a process. The process again there should process on that cluster specification. If you see SPT abstract, you are not specifying those endpoints in each and every process. So you need to make change only in one cluster and it automatically reflect in all the processes and the fields which are using or are dependent on that cluster. How should the process run? What are the parallel instances which can run? What is the order in which those instances have to be run and how frequent those instances have to be run? And this is the input field. It says the field name is legit enhanced, is the name is specified. So all these cluster process and fields, they use names which is specified here as their ID for identifying which field or which process, which cluster are you trying to refer to. So in this case, it's trying to refer to text enhanced field and has a start and end for the input range and which partition of that field is trying to consume. And then it has what to produce. So the event in this process consumes text enhanced field and produces field field. Then we also specify replies. So in case of failures, how many times you want the reply to happen. And you can also configure various policies for replies. Do you want after every 5 minutes, or do you want an exponential backup policy? Let's say first time you want for 5 minutes, then next time you want 10, third time you want 20 minutes later on. You can specify those policies. This is very configurable. You can just specify it here, and Falcon will take care of replies for you. Then this is the part that I was saying, late data handling. Here to specify, this is how I want the late data to be handled. In this case, we are saying, if this particular field comes late, what is then reproduced, so Falcon will keep a track if this data has changed. Then, if you want this process to run, and this is the workflow which we use, you can specify a different workflow you want to use for late data handling. Let's see a little bit of architecture. So this is higher architecture or very simplified version of Falcon's architecture. So we have Apache Falcon, which is a Falcon server. And in this, you have there's a CLI endpoint and then there's a REST API endpoint. So you can use the command line interface for filing commands, which are entity or instance commands. So you can query the entities or the particular instances of an entity through the CLI or through REST API. Then in turn, Falcon has a config store, which is an HTTP Falcon store, so it's configurations, basically the definitions of all your entities, process, field, and cluster. Then we have a workflow engine. In this case, it's Uzi. You can replace it with any other workflow engine. So this is Uzi. And Uzi uses /log. And we have one messaging endpoint, which you can use ActiveIQ or any other JMS compiler, which will be used for sending out notifications which Falcon consumes from the workflow engine and then sends out to the user also. So this is the low level view of the architecture. Then consider pipelines. You want to wonder how much comes is testing. So Apache Falcon helps you in that also. This is a framework on your Falcon Unit, which is a pipeline direction framework. You have written your pipeline processes 1, 2, 3, etc. And you want to validate that the data that they are producing is according to expectation. So these are some of the use cases which we use for pipeline testing which we have, and that is the reason why we created Falcon Unit. Falcon Unit has a test suite which runs on Falcon Unit, and Falcon Unit can run against an actual cluster, which you use for your staging environment. And in local mode also you can specify where to use the local file system, etc. For development environment or your integration tests. This is an example of a process, so you can give it a path, a definition, and you can say I want to submit this process, like this is the local mode, and in the same way you can specify the custom mode as well. So same API, you can, this is as easy as like this line to schedule the process. You specify this is the name, this is the start time. I want to schedule these many number of instances, and I want to schedule them on this system. And this is how you can verify the status. What is the status of the instance? Status successful, instance unsuccessfully or not. Then there is a UI. So Falcon, all these things, Falcon has a very nice inbuilt UI for all these things. For example, there is a UI to build all the XML definitions, which you can create them offline and submit them to Falcon through CLI or SAPI. But you can submit them to UI also. So UI will do replace validation, etc. So any newcomer can start using this and create new entity definitions. Create custom definitions. You can search from the UI. Then there are some out-of-the-box recipes which Falcon has. For example, if I want disaster recovery recipes are written in Falcon, you can just specify some configuration and Falcon will automatically do the disaster recovery based on HTTPS, and there is a recently added high HTML based disaster recovery also. Then in deployment, Falcon has two modes. One is a running mode in which there is only one Falcon server instance, and then there is a distributed mode which we use at Hadoop. There are several tools, several data centers. Each data center has one Falcon server. And then there is one Falcon server which is called Falcon Bridge, which just takes your requests and sends them to respective players and needs to send those requests. So if you do some smart filtering on around 90% requests and will send those requests to those Falcon servers and will aggregate the response back and will show you the concept you can do that for all the data centers. Then for monitoring, you have SQL monitoring. We have data monitoring based triggers, we have dashboard APIs, we have probably the learning system, you can configure to have events or certifications for your monitoring purposes. And this is the pipeline which I was initially telling you. Here you can see that this process speed, which is consumed by this other process, and then this data is consumed by this process as well as this and this. So if you are planning to make some changes to this, you immediately know what are the entities which will get affected. If this output is changing, anybody changes in these processes. There's another very interesting feature which Falcon has got. So let's say one of your particular instances as one node, since there is a data relay concept, there will be, if one instance is failed, all the subsequent instances will also fail, and you will be like provided with alerts. So when you come up online and you want to see where exactly is my instance failing and why is it failing. So in this case, we use the dash API. This will show you that the instance of feed 3 is failed, which is produced by process 2, which says feed 1 and feed 2 is equal. Feed 2 is green, which means it's available. Feed 1 is not available, which was produced by process 1. So you know, for example, this process 1 is incomplete. If you just restart or rerun this process, the entire pipeline will be unblocked and it will run on its own. So that's one of the very powerful development features which we have. And in the end, cursor roadmap, we are adding more features like authentication, authorization. We are adding more features to the UI, and even more adding like process SLAs for better monitoring. Like if the process doesn't start or doesn't end in the specified time, I want to get alerts. Same planning alerting system. We are also working planning on streaming support. We are also working on a more powerful scheduler. So OC has scheduling capability, which is like third-party mechanism. But in a lot of cases, which a lot of other cases, OC was not sufficient. So we are running on a more latest scheduler, which is far more powerful than the OC scheduler. And the pipeline recovery based on capacity and priority, and our pipelines to be scheduled automatically. So these are some of the works which are in progress. And last but not least, partners are very active and very open and very long community. We should engage to welcome if anything responded to requests for us, partly because not all the developers are in US, some of the communities in India. And most of the times we see Shrikant himself responding to the emails. And we are looking for contributors. Every contributor is welcome. All the committers are very, very willing to help. So, give it a try. Questions?
A lot of pipelines are actually using Kafka and Star, like for things. So a lot of pipelines actually use Kafka Storm. Do you have support for Storm as well? Like we wanted to find out topologies in Storm itself. So.
Yeah, that's a very good use case which you mentioned, and we are actually working on that, which I mentioned, the scaling support. That's for exactly that use case. We are currently working on it. It's not available as of yet, but very soon.
So would you have to, just a follow-up question, so would you have to define the topology in Storm itself or define as an entity in Falcon? Like,
so we haven't yet figured out the meeting ready, but we are still working. There's a discussion that we just started that we want this, and soon we have a design document ready. But it will be very good. Any other questions? Yes, thank you.
So next speakers are from today, they will be presenting the big data use case, what we do at eBay. So Vishal and Vijay will take up this session.
Here, I'm Vijay, and I'm part of the logging team of eBay. So this talk is about how big data can be, and we are taking eBay logging as a use case. So in the beginning, there were a bunch of web servers, and the eBay gods decided there's that logs. So in the early 2000s, we came with something called decentralized application logging, the V1, and it was written in C++. It was primarily 32-bit. We had our own CAL client with which your application can basically write logs into CAL. So we follow the concept of structured logging. By structured logging, what I mean, by structured logging, what I mean is that say you have you are accessing eBay.com homepage, and it does a bunch of stuff. It calls a few service calls and all that. So all the logs are bundled within one transaction. So it has a level, so level 0, and we have conventions like small t, capital T, where we say it's the beginning of the transaction, the end of the transaction, and E notifies the next event. So each CAL record has a type, a name, a status, a duration, and a payload. So in this transaction, the type is URL and it's eBay home, and it has done a few things. So basically, what developers do is, so they take class name as a type, method name as name, and with that they write all the CAL logs that are required. So this gives you a holistic view about what is happening in your application. So if there is an error, we give the versatility for a developer to basically dump the entire stack trace in the payload as well. So with this, we are able to achieve a bunch of applications that are there, primarily reggae search. So if you have say 100 app servers serving eBay home, and there are a few exceptions that you want to catch. So regex is the best way in which you can do it, where it will run the regex across all machines within the bunch of app servers that you own. So we also provide web analytics. So to our CAL, all the history data flows through. So in case you want to take business decisions like which is the right place to place a button. So this click through information can basically say, okay, this is a good place, this is not so good place. So there is life side experiments that go on where 10% of the users are exposed to some feature, and the clickstream data basically the closed loop can is used for taking decisions that impact the business. And we also generate reports. So for a group of application servers that are serving say eBay Home or whatever, what are the number of URL hits that were there, what are the number of errors that were generated, how many SQL statements were called during the entire hour or entire day, all that we generate in the form of reports. So here are some of the challenges that we have. So this is a little teaser about what is the eBay scale that is there today. So we get 7 billion URLs per day, and that incorporates greater than 150 SQL statements that are being executed. An average user spends an hour on eBay, which is 3 times more than any other American online retailer that is there. And at any given time, there are 800 million listings that are there on eBay. So in last Q2, we did $20.1 million worth of transactions last year. So this year. So that is the scale at which we are operating at eBay. So our data centers are huge. In production alone, we have more than 60K web servers that are there, and all of these actually log into our centralized application login. So as time went on, there were logs, then we generated more logs, and then we generated even more logs. And logging volumes grew 100% year over year. Today, the current uncompressed logs that we get is 400 terabytes worth of logs per day. So our system is actually taking 400 terabytes worth of uncompressed logs every day. And these are all stored in filers, NetApp filers. And filers, as you know, is very expensive, and we could not accommodate to the growing log volumes that were there. Since the applications were 32-bit and transaction sizes started to grow, we couldn't hold everything in memory and process it at any given time because it's 32-bit. And so as the logging volume kept on growing, so we do generate RD reports that are there, and these RD reports couldn't complete within the hour. So it got spilled over and then eventually it started queuing up. So the time to complete processing also grew rapidly. And nothing was API driven. So these reports that were being generated, they were all HTML files that were there. And customers, what they did is they actually started scraping the HTML files to do their own automations on top of these reports. So we decided we need to write a new chapter. So right now, Hadoop, what we did first is we started using the HDFS. We started dumping all the log files through a batch that was triggered at the end of every hour when logging completed. We dumped everything into filers. There was three-factor replication, which gave us the fault tolerance that we needed. And since it is commodity storage, we were able to save a few million dollars on that. And today, as you know, the world is Java. GitHub today runs Java is the second most popular language that is there out in the market, and we changed everything to 64-bit. And we do MapReduce there. So we ran Redis on MapReduce, we ran report generation on MapReduce, and we also exposed custom log processing through Pix scripts as well to our customers, so that they can generate custom reports of their liking. And when you're done, just throw everything in the form of REST APIs, so customers can not scrape it to HTML. So this is the current application that is there. So all the app servers, they log in, they push all their logs to something called CAN publishers, and that in turn drives into a real-time bus as well as persistent storage, which is filers. What we do is we take all the log files at the end of every hour, we ingest it into Hadoop, and through that we have a set of applications like regex, reports. We have a log view application where customers can view their logs at any given time, and we expose this all through the MapReduce and Pix APIs that are there. So is this the end? No. So these in turn, what they did is they exposed the two challenges that were there, and we ended up solving these challenges, which are mainly the log ingestion at terabyte scale. This had two problems that were there. One is the too many small files problem, and other is bringing batch closer to real time. The second one was self-serviceability. Now that we had APIs and all that, we wanted to onboard our customers in a manner where the team did not have to involve themselves. And fast scanning of log files, our log files can go up to 2 GB worth of uncompressed logs per hour. So these 2 GB to scan for a particular event, we should not be wasting too much time, because in a site outage or a very mission critical time, users must be able to get it within a matter of seconds. So with that, let's move into the first problem, which is log ingestion at scale. So there are two problems that we are solving here. One is we have 400 terabytes worth of logs per day, which translates to 80 terabytes of compressed logs and 5 terabytes covers logs per hour of the peak hour. So 12 hours is considered as eBay's peak hour by eBay's statistics. And we wanted to provide the users logs at near real time so that they can run logs, run MapReduce on their logs even at a 3-minute SLA. So what happened was initially when we started off, we took all our log files and we put them directly as they were generated into Hadoop. So what this triggered is that we noticed that more than 60% of our log files were of size less than 10 MB. And with our block size being 128 MB, we were actually doing a very bad job in increasing the amount of metadata that the name node was holding. So at a given time, for per hour, we were pushing around 400,000 log files into Hadoop. So as you know, the name node actually maintains a metadata index of what are the blocks that are available, what are the directories, what are the files, which data node it belongs to, and all that. So as the number of files that we pushed into Hadoop kept growing and growing, the amount of metadata that the name node held at any time was very high. So our cluster actually held metadata worth of the order of more than 80 GB at any given time. So our name node, we tried to increase it more than 110 GB, but then we decided that's not the way to solve it. We need a better way to solve it. So what we decided was we decided to put all the files of a given app server. An app server can generate anywhere between 1 to say 200 files. We clumped all of them together and put them into sequence files. So that was the solution that we had gone for. So we ended up using Zookeeper and a distributed worker setup that was there. The distributed basically what it does is it tries to identify what are the log files that need to be assigned for any given worker, and the worker will basically do the process of creating sequence files out of the log files and pushing it into Hadoop. So the solution we leverage Zookeeper for orchestration. We use the sequence files, and what we did is at the end of every 3 minutes we were pushing data into Hadoop. So by doing this at a 3-minute interval, we were able to get the log files into Hadoop at a much faster rate. And what we did is we provided current support for MapReduce as well. Today, when you try to do MapReduce on a file that is open, you will not be able to successfully run the MapReduce job because the get length method of the file system will always return 0. So actually, what we have done is we have extended the file system APIs to get the actual length from the DFS client and pass it on to the MapReduce APIs, so that even when the files are open, you will still be able to run MapReduce. So this is the basic architecture that we had gone for. So we have a distributor and we have a bunch of data copy workers that are there. All of them talk to each other through Zookeeper. The distributor, what it does is it identifies how much workload is there and it creates Zookeeper nodes. And the Zookeeper nodes are registered to workers. So if you look at the diagram over here, so for every R we create an R level directory, and within the R we create one directory for every worker. And within that we tell them, okay, this is the application server for which the logs need to copy. So the worker what it does is every R it finds out what its workload is, and it will take all the logs that is there from Filer and start copying it into Hadoop. So what are the wins that we achieved from this? So the file count, which was 140 million, we drastically brought it down to 20 million. And the memory usage, we had a 40% improvement and brought it down from 75 to 45 GB. Because the number of files were reduced, the metadata imprinted on the name node came down drastically, and storage was never an issue for us because the size of the name node heap there was always an issue. So since we brought the heap down, we were able to increase the log retention for our customers from 15 days to 30 days. Here are some interesting statistics that are there about our data ingestion framework. So any given worker can compress 300 GB of uncompressed logs per hour, and we do 400 GB worth of uncompressed logs at any given day. Our workers are very resilient; they do not go down at any given for months, and the setup is entirely fault tolerant. So what happens is if a worker goes down due to say hardware failure or the Tomcat goes down, what happens is the distributor is always aware that the worker goes down because they all register ephemeral nodes onto Zookeeper. When the ephemeral node vanishes, what happens is the distributor is informed that the worker has got down. So what it does is it just picks up all the workload that was assigned to this worker and just distributes to the other workers that are there. So that way, if one machine goes down, there's nothing, so there's no loss to us. We can always bring the Tomcat back up. If there's a hardware failure, we can still use with the remaining workers that are there. So we are able to stream logs with a latency of 3 minutes, and thereby helping our customers to get logs from Hadoop within 3 minutes. And this greatly impacted the health of the cluster. The cluster used to go down every other week or every other month because of the amount of metadata it was holding at any given time. With this change, we have never seen downtime because of the name of going out of community. So with that, I will hand it over to Lucian.
So I'm just starting with like this general respect to big data. Yeah. So I'm sure you all be aware of what is Apache Pig, right? You must have used Apache Pig script, right? But you must be aware that what's the real challenge is when you want to use Apache Pig in the shared Hadoop cluster environment. Then you have lots of customers who want to onboard with Apache Pig script, right? And so at the time what we have is a user who wants to use needs to find running Hadoop represented granted access as it has to be submitted only from the CLI machine, right? So that is one of the challenges to provide the access for the customer. So another thing is something like that. You cannot control like amount of jobs being submitted by the different users, right? So if you want to control that how many jobs can be submitted by a user or what is the rate limit and all those things. So those are the some limitations which is existing with respect to current Apache. And one of the things is that as we move from the like old can framework to the new framework, we also want to like users themselves get onboarded with that kind of environment of the customer reports. So we don't want to get involved with whatever kind of customer reports requirement they have. As Apache is a sensitive thing, user can write it whatever the way they want to write it as it is accepted in terms of development libraries. So we just want to onboard any new customers with respect to that. So what we thought is that why not provide the REST-based API interface for the Apache itself? And that's what we have done for Mike as a project, which provides a REST-based API interface for the team. So what are the interfaces available for the team, right? So if we are writing your own kind of a UDI, right, and if you want to basically store your jar file, so the first set of API which you can use is basically deploy your UDI jar. Second, once you have written your big script with your kind of a custom logic requirement, if you want to deploy your big script, you basically use the same REST APIs like deploy my big script. So these are the things which will get stored within the Hadoop itself. And now if you want to run your big script, you just say that just execute a post command saying that this is my big script with the required input parameters whatever you need to submit along with that. There are also other APIs like you can find out what is the current status of my big script, whether it has been completed or not. What is once the job has been completed, if you want to find out what are the different statistics around that, how many jobs submitted, what is the number of input records, how many number of output records. So there is a specs in place for that. And then also something called output API. So what is the peak output? What is the peak jobs output? You can also get to the guide for receipt. So what happened after doing this fixing, right? So there was a zero vendor information or there was a monolith or a guarantee from the Hadoop team required any kind of support to onboard any user with respect to fix script. So and as it's a REST API input, right? So if you want to control, if you want to provide any kind of rate limit, if you want to provide security access, that is the place where you can provide all those things with the REST API interface. It also supports multi-tenant. So if you have a different type of customers accessing the same Hadoop cluster, you create a different tenants for the same user will basically log in with respect to that tenant. And another thing is that as a user who wants to onboard with that, you don't need to know what is the Hadoop cluster specific information, where is name node, where is job record, or resource manager, where is yarn, and all those things. And for that matter also, as generally as you are the peak script generally comes as a single JVM, but as it's a REST API interface, it's being deployed under the target and runs as a picture. So we have basically done some modification with the peak source code itself to make it run under a single JVM with multiple requests. And yes, it's open source. If you guys want to like to explore it, if you want to do commit, please go ahead. Second thing, sorry, yeah. So some of the steps with respect to that, what is happening? So we are able to unload like more than 100 unit scripts without actually, as a team, we are aware of that who is using and how they are using. And we are right now running like more than 6,000 peak jobs daily, having more than 100 unique users, and no unloading. The second thing which I'm going to cover is about lookup for a log file, right? So consider a scenario that there is a site outage. You get an error saying that there is something wrong with your particular application or particular machine and at that particular time. Now what you have is all the log files. Log files which are being stored in the compressed form, and as you can see, it can grow from say few megabytes to few gigabytes. Now if you want to find out what your application is logged with respect to that timestamp, generally what happens is that you basically go and your application will go and uncompress and log file, look at the particular timestamp of the log, and then find out okay, this is what something might have happened, right? So that is a lots of time being wasted in the side of the situation, and which basically you all do like that. So what is the something like what from is along with that, right? So suppose you have log files and store somewhere else like Hadoop kind of location, you will have data transfer is happening, and compression is happening for the same file to return the particular log. So what are possible ways to basically avoid this kind of thing, right? So as you know that we are looking for a particular timestamp of the log, just try to go and basically jump to that location with some relevant information which might be available to you. Along with that, once you do and jump to that location, and if there is a data transfer required, just transfer only that portion of data, like a few minutes of data or maybe few seconds of data, and then just analyze that data rather than transferring and passing the entire log file, right? So what we have done as part of that, whenever we have a compressed file store, either as a gzip file or even say the sequence file itself, right? We have kind of expose some kind of APIs where user can basically create an index within the file, right? So the index which provides that, suppose you have a simple example of a log file, it's an hourly log file. Every minute you kind of create an index that what is the current byte offset in the current log file, and you basically maintain that as an index. That okay, first minute of data is written at this location, second minute is data is written in this location, and that index will be again written inside the same file. How we can remember? We'll just walk you through it. So, as you said, this is a gzip file. So, this is a gzip header. So, as you might know, that a gzip file has some header associated with that, and it can basically write multiple headers within the same gzip file, right? And there is some provision, something called there is a flag called a flag, where you can mention that along with the standard header, if you want to write any extra information, you can write as a part of the comment section. That will be the last portion. So here, if you feel like if you want to write any extra part of apart from the comma header, that is what you can write. So how we have used those fields? As a set of APIs, whenever you are basically creating this gzip file, user can just index and then okay, create an index for this particular minute. So suppose in first minute or second minute or third minute, and what is the current bytes offset for the minute? Based on that, the information will be written inside the gzip file. The similar kind of thing what we have used for the sequence file approach. So basically, say this is the sequence file, this is the sequence file data, and you have key and value, right? Now, in between, if you want to create a kind of an index for every unit of data what you are writing, so internally, when you basically create the sequence file, it is going to maintain those kind of an index, and at the end of the sequence file, we are going to write an extra key value, something called a trainer, and it will basically point the entire index of the data. So that assuming an example of several log, you will have like 60 indices will be written, one per every minute, and then every minute will point to what is the byte offset. So as you can see, you are supposed to say this is what the index is written for every minute. Now suppose you want to jump to the 20th minute, suppose the average is from the 20th minute, and you want to directly read only the 20th minute of data. So this can basically say that 20th minute data has been written at the byte offset say XYZ. So you basically directly jump that, and you start reading from that, that will give you only the 20th minute of data, right? Now, if you have a very large volume of data on log file, if you want, you can further break down and basically say that, okay, that will basically point for some kind of the index again, which will be like index at the second minute, right? So for every second within that minute, if you want to write a kind of index, that is also possible, and based on that, you point, okay, if you are looking for this minute, this second, this is the byte offset which you need to look for, and which will provide you the data for the same. So, with respect to this approach, as you can see that right away, okay, GC for sequence file is good, why not HDs or why not once a map file is implemented maintains the index, right? So these are the some of the pros and cons what we come up with, right? One of the use cases which I just want to mention, right? So generally log files are getting generated for a particular application or particular machine or particular power, right? So it is already kind of a partition for data, right? So you don't need to do further partition. Now, with respect to this, what happens is that basically, whenever you want to compare in terms of performance, we have mostly seen that the performance is nearly same whether you do from the HKS or whether you do from this index-based GZIP file. Only thing is what you need to do is that first you need to jump to the end of your GZIP file and read the index data, which says that what is the byte offset, and based on that byte offset, you basically jump to the location where you are looking for. The second part is, as I mentioned, the index are written at the end of the file. So basically, you need to read, you need to wait till the end of the file is reached, and then only you will be able to read the index. So kind of current support is something may not be there, but again, there are some other way you can keep on passing the indexes every now and then. You should be able to read the latest index also. The main challenge if you want to use the HKs, right? So basically what happens is that if volumes, the number of keys grows, right, you will have a regional speed coming, regional going down. So there are kind of like instability issues which can be faced when you have a very large number of data. But with respect to the GC part of sequence, it is already demonstrated, you will always go and read it. And similarly for the security aspect, if you are looking for high retention like 30 days from what I mentioned, then yes, the number of keys will be very large number of okay. So what we have achieved when we do this, right? So if you look at this graph, right? So what happens is that the blue line is what the time taken with respect to the different complex files of 1 MB, 40 MB, 70 MB, up to say 80 MB, right? So suppose I want to look at the particular minute of a log file. So here we have taken an example. Suppose I want to look at another 50th minute of data. So these are the time taken in the normal GZIP file, which maximum around say 30 to 40 seconds. And here also we are using the kind of the seek operation which is available in the GZIP. So suppose say given say 280 MB file, if I directly jump to somewhere around say 200 MB in the GZIP and then start reading from that, right? But what is going to happen is that in that case also the uncompression is going to happen for the entire file, right? Now with respect to the index levels, you can see it is nearly taking almost the same time with respect to the time to size because the time what is going to happen is that just read the index from the end of the file and jump to the byte offset what you are looking for. So with respect to the size of the GZIP file, it gives much better performance compared to the normal GZIP. So as part of that, what we are planning to do is that we are working on this project called GZIP, which is going to provide you the same seekable interface for you for the GZIP file as well as the sequence file records. And we have the different classes exposed for that. So basically, this is GZIP output stream record access, which you need to use to create those kind of a GZIP file, which will eventually maintain the index file. And once set of files generated in that format, you basically use this GZIP input stream record access to read that. Similarly, if these kind of GZIP files are stored in the Hadoop, you basically use seekable GZIP data input stream that basically extends the Hadoop status data input stream object, and you can do that kind of thing. We are also using this concept to provide the splittable GZIP code. So currently, GZIP files are not splittable in the Hadoop, right? So if you want to split the file of GZIP file, how you can do that? So as we are going to write multiple headers inside the GZIP file, you can basically break either kind of whenever the new header is going to start, right? So that is what we have done. We are going to expose as a splittable GZIP code, and you will be able to split the GZIP file. So it will be going to be open source soon, maybe in the coming month. So this is all about with respect to the big data, what we have achieved and what the different things we have done. We would just like to share some of the common things which might be useful to you guys also. So first of all, something like say whether it is assumed that Java is considered to be as good as kind of native code, but for some of the scenarios we have not seen that kind of thing. Maybe like when we are talking about the native code, we have seen that if you use the native combination libraries, it basically gives much like 5% bigger performance compared to using the Java's combination code. And whenever you call it big data, as you mentioned, kind of small files, generally what you encounter, so it's mainly made for using the larger number of data rather than the small files. Similarly, if you are doing any kind of a string comparison with the Java code, right, you may have to do it the byte rather than the linear string. Because it generally it's highest number of object-oriented classes. The one with the weak, what we found is that yes, it is generally a command line to run with the single process and all those things. But if you want to run it multiple big jobs, and in order to avoid the JVM, you need to do some basic things to that. And when everything is such, yes, please think about the rate part and maybe something kind of a relaxation. So, I'll be there yet. We are on the journey, we have not reached peak yet, and in order to reach there, so we are ready. If you would like to join, please.
Which is a the last topic from
Hello.
No, it's not there. Can you show the picture? It's not there. Which one?
It's a PDF, I guess.
Oh, PDF. PDF. This.
Hadoop meetup Bangalore PDF.
Oh, okay.
Huh?
This one. What screen?
Screen.
Hello. My name is Sunam Raju. I am from eBayBigdataMeetup and I'm here with my colleague Jagdish Mohan. So we'll be talking about dynamics of benchmarking a query store for hosting terabytes of data. So first of all, what is such a topic? That there are many query stores already lying out there. HBase is there, Cassandra, Hadoop, MongoDB, and whatnot. So why do we have to care about benchmarking a query store? So first of all, for all the problems, there is no one solution. Multiple problems will be there. You will have to find your own solution. Because if you look at the catalog of HBase or the catalog of Cassandra or the catalog of Hadoop, everybody will claim they are best in the world. So everybody will say that they are giving a throughput of 1000 kbps from a single machine, from a development machine. They are giving a read-write throughput of 20,000, 40,000, 60,000 kbps. So when all these options are available, how do you choose that this is the query store which can cater to my needs? One very basic thing is there: throughput. When we talk about throughput implicitly means that you have a payload associated to it. So in any query store, let's say for example, if I take HBase, it is saying my throughput is 1000 kbps. The notion of payload is there. Just say for example, if I say my payload size is 1K, then I can provide you 1000 kbps of throughput. The moment I make my payload as 25, my throughput will decrease by 25. So that is the problem. As in, everybody will have their own use case where they will want to have where the payload size will be different, and so you will have to choose your KB store by benchmarking it so that can it cater to your use case or not. We at MOB have a unique challenge because we are serving around 8 billion requests arising from 1.5 billion users, and we want to pivot the data of a user and store them into some KB store so that in millisecond time we can get the holistic view of that user, so that we can do real-time analytics
we can do real-time profiling, which can help us to boost our network. As in more relevant ads we try to show, more money will be generated. So this is the basic agenda. So we'll generally go, we'll go with the against the big table, the Linux commands which will enable us to benchmark, the best practices, and the common mistake that we did, and what we think generally most of the people do while benchmarking anything. Okay, I would like this session to be quite interactive because this is the last talk. Many people will lose their info. So maybe after 15 minutes we'll have a interactive session. So please hold on to it with me, and I'll just let you go through some commands and few different perspectives of looking at the general things. Just as for example, top command, I will give you a very different perspective of how to look at top command, and then we'll have an interactive session. So please hold on and hang on with me. This figure looks quite similar, as in you have one cluster and you have 6 Hulk nodes out there, and you have one personal node. As in all the Hulk nodes, they have a lot of resources, and personal node is also the same. The only thing is it is not doing properly. Now I submit a job in my cluster, and the job is equally divided among all the 6 Hulk nodes and personal node. What will be the completion time of that job? Who will be deciding the completion time of the job? It will be the company. Why? Because he is the slowest, so till the time he doesn't complete, your job will not be completed. So this is one of the perspective. If I am seeing my cluster from top down approach, let me take a different perspective. I am looking at my cluster from bottom down. If I take one node from my cluster, and if I take my application, if I am able to queue my application properly with that node, whatever the queuing parameters are, if I apply those queuing parameters across all the nodes in the cluster, then all whole of the cluster will be only comprising of Hulk nodes. There will be no company. And the throughput that I will be getting from my cluster will be max, because I will be utilizing my resources as in CPU, your memory, network, and everything to the max limit. Will be extracting out the maximum resource utilization from the cluster. The intent of this talk would also be that by the time I finish this talk, just by looking at the architecture, we should be able to figure out that, hey, here is the problem, this is the maximum throughput that we can get out of this thing. So I will be briefly going over the big table architecture, what it is in general, so that it becomes more intuitive as and when we go further in the talk. So a big table, a small table in SQL will look something like this. So we have the primary keys out there and some columns out there. So what is big table? You shard one table horizontally. So that becomes something that you can host on a reason server, because small set can be hosted on a single machine. So if I am able to correlate, how many of you are aware of HBase here? Okay, fine. So let's try to visualize. If this table is some terabytes long, then that table cannot be hosted on a single machine. So what we can do is we can shard that table horizontally. The moment we start sharding the table horizontally, the small shards, they can be hosted on one single node. So that becomes the reason server. You can also shard the table vertically, so that multiple columns can be grouped together inside one shard. So that becomes the column family in your address world as a big table world. So a very high level overview of what is happening here. So that was the client, that was the master. HBase works on the master slave nodes. It's not like all the big table KD source. Just say for example, etc. That doesn't follow the master slave concept. That only has the master concept. So just in case of HBase, we are having a master which will do all the administration job, as in load balancing. If one reason server goes down, all the shard that was allocated to that reason server will be moved to somebody else. So you have the real servers. This is one thing. I don't know. Thank you. Yeah, this part. So this is the research server. So this is basically one node. These edge files, they are basically column families. So you have one store which represents one column family. This is the second store which represents the other column family. This is the H log which represents the val, that is right ahead log. Even in SQL world you have the right ahead log. So to prevent if in case of any crash or something, data is first written here and then it is moved into these stores, which ultimately goes down and lies in the file system present here. This is the in-memory store, which is known as mem store, and the file system here is not the normal file system, is the distributed file system, which is DFS. Fine. A given node. The only resources available with a given node are these: CPU, memory, storage, and network. Whatever you have to do, you have to try the maximum out of it. At the same time, you have to make sure that everybody is doing some meaningful job. It shouldn't happen that you're utilizing your CPU to the max, as 90% CPU utilization is there. And the only thing that you are doing out there is you are just doing value selection. That doesn't make any sense. So we have to make sure that all these resources are performing well and they are doing something meaningful. Let's go on to some commands with a different perspective to figure out how do you measure that each of these components are doing good and have you tuned them properly or not. Command here are Hadoop systems. Just in case you're using some other system, please try to figure out your counterpart in that one. So we'll start with CPU, memory, storage, and network. So in the same sequence, we'll be going through the commands. Top command. So the moment we go to the top command, we can simply figure out how much is the memory usage, CPU usage, resident, and shared memory. So what is so special about the things that I have marked in red? I would like people to take a shot. Like, what is so special here? As in if somebody is looking at personal memory, are you making any sense? Like, are you using top command to really figure out something good or bad? As in, is that even of some, is it even relevant or not to you? So mostly virtual memory is in most cases irrelevant to us, because virtual memory is what? It's like the complete memory map of that process. As in, whatever files is holding, whatever is there in the stock space, whatever is currently there in the RAM, is cumulative of everything. So just in case you are looking at the virtual memory, you are not making much sense out of it. What is the resident, and the resident part is what you should be looking at. As in, if I am saying my JVM, I have spawned with a XMS of 1 GB, most probably my resident memory should be 1 GB there. As in, for that particular process, resident memory should be showing 1 GB. Fine. If you look at the virtual memory of that process again, it will not be 1 GB, it will be much more than that. This is what they claim is being used. This is free and this share buffered something as cache. Again, we have the next line which talks something about this. So at this point of time, if I say how much memory is really in use, as in if I want to respond to the process, how much free memory is there? How do you interpret this and which one take? Should I take this free one or should I take this one? The first one or second one? Let me make an interactive, that's okay, because otherwise it will get very boring. The second one. Fine. Yeah, this is the second one. Why not the first one? Because the first one excludes the buffer and the cache memory out of it. So what is the buffer and cache? In the OS world, whatever you read and write, or whatever you're reading and writing over the file system or over the socket, that becomes part of your buffer and cache. As in, at that point of time, that memory is in RAM, but if required, OS will free that memory and you can use it. So just in case you're writing a file of 1 GB, that 1 GB will be saved onto the disk at some point of time, not instantaneously first of all. And secondly, if you are reading back, you will be reading back from the cache. You will not be reading back from the hard disk drive. So that will give an advantage because memory was free. This is the OS optimization. And page cache is the most efficient cache that has been built up. So in general, if you can have enough of RAM, you don't need to build your own cache. Like whatever cache you're building is just an overhead. You can rely on page cache if you have extra and free RAM available. essentially where most of people go wrong while doing benchmarking and they have no clue what's happening here. So your network interface card, it itself says what is the link out there, as in how much link can it support, as in how much Gbps can it support. So using the F2, you can figure out what is the max available speed that you can get out of the Ethernet card. Just for example, it can be 1 Gbps, it can be a 2 Gbps link, whatever it is, you can figure out that from here. NS over clients, I will tell you about all the open ports on the system, as in who is using what, which process is binding to it, which process is listening to it, how many sockets in total are present out there. Open sockets are present out there. So this is a very important indicator just in case you are benchmarking or you are running into some kind of troubleshooting. Because you can land up in a situation where clients are simply bombarding your machines with some kind of request, opening sockets, not closing them, and as a result, your server is not able to scale up because it cannot accept any more corrections from the client. Now let's take an example wherein you have one server and multiple, as in one node and multiple clients. In that case, if I want, just tell me between this client and the server, how much data is being transferred at that point of time. How do you figure that out? So it is with this command. If top will give you at that point of time how much data is being exchanged between node 1 and node 2. So this is very important. So let's take a real world scenario that you would have faced in your production also, that one server is there or maybe one DFS node is there, it has been connected via multiple clients. You are saying, hey, my node is going down just because I think somebody is flashing the network. But you don't know which is that client out there. In order to figure out that, if top is your friend. CPU.
The network shouldn't be considered whether it is full duplex or half duplex.
Yes, a very good point. Sorry, I missed that. You should consider it's a full duplex or half duplex. Because the moment I say it's a full duplex 1 Gbps means read and write both are having 1 Gbps. It can support 1 Gbps. If it's a half duplex, it's just 1 by 2 on both sides. CPU. We'll get back to this point later also, but as of now, this is a command with empty stack, which will provide you information about all the CPUs that are present in your machine. Because generally on our machines, it's not only one CPU, it's like a 24, 25, or maybe 36 CPUs are present there. You want to track at this point of time which CPU is doing what, how much memory, how much utilization is happening. But again, you have to be very precise in saying that the CPU utilization is happening, but it is happening fruitfully. As I said, what if your CPU is just running the garbage collection threads, it's doing nothing. In that case, your CPU utilization is happening, but it's of no use to you. So we'll figure out how we will figure out that. Disk. Probably the part which has been left out by most of the people because we just assume that okay, fine, something is happening in the background, somebody is just going ahead and selling by file. Nobody really knows how you can even go and tune them, and even for what use cases. That is what distinguishes this as compared to because ROM, CPU, maybe network, everybody is quite aware of these things. But this, people don't even care. Because we simply think that DFS is an abstraction over us, I don't know where the data is going to reside, what is happening. But this can itself become a very big killer for the whole cluster, and in our case for the KB store itself. Because you cannot hold even like if you are having a 200 terabytes of data that needs to be saved on a KB store, you cannot you can hold 200 TB of data on the RAM. You have to hold it on the disk, and on use case basis, you have to pull a bit onto your RAM and you have to serve it. So you have to tune this particular thing. Else you can never think of that. Okay, fine, I can have this KB store has claimed 1 millisecond latency for every request out there. So I will be having 1 millisecond irrespective. I am having 1 TB of data or 200 TB of data. No, that will not survive. As in that's not a scalable one first of all. Yes. Let's do a quick session. How we just figure out how we discard the machine. So there is something that is defined as etc/etc tab. It will simply tell you I am having 6 disks. It will also inform you that on a given disk, which is a root partition, on which disk you have gone ahead and registered your swap space also. So the easiest command to figure out all the disks on your machine is fdisk minus I. So it will simply say on your box, these are the disks, these are the spaces for those given disks, and what kind of partition it is. Is it ext3 or ext4, whatever it is. Just like in RAM, OS has its cache, the disk by itself has its own cache. So whatever you are reading or writing is not as big as the RAM cache, first of all. It is very less than that, but it can play a huge role if you can tune it properly. As in, if you know that, fine, in my use case, I am always going to read maybe 200 KB of data, like my payload is 200 KB, and I am always going to read back whatever I have written back. If you can tune your disk cache to hold 200 KB, you can really make a lot of difference out there. Because your data is always on the cache, it has gone to disk, but by reading back, OS will first try to read from the cache and then from the disk. So you can make a huge difference if you can tune this particular parameter. Those two commands, block def minus plus def and sdpara minus f, they can be used to flush your disk cache. Let's get back to some more basics. How do you figure out what is the block size of your disk? Don't worry, we'll even go ahead and figure out why are we going through all these things, because they will play a very important role when you are trying to do benchmarking and trying to do the analysis over data you carried. As in, you have done the benchmarking, now you want to connect the dots. I have got a QPS of XK QPS, now let me figure out how my disk was performing. So at that point of time, while connecting the dots back, you need to know what all these parameters are. So the easiest way is the first command, ls block minus whatever is present there. It will simply print the disk block size. So technically the disk block size runs into 512 bytes. The last two commands out there are to test what is the read and write speed of your disk. So just in case you are working on an AWS cluster and they claim that I am providing you some 500 MB per second worth of speed. Before doing anything, go ahead and run this command. Because what they claim and what is being offered to you can be very different. It can be so different that it can screw up the whole benchmarking or whole TJ task of yours, whatever you are trying to do. Fine. So this is for SSD, but this can even be tuned for SSDs also. So let's try to imagine something about this scheduler. So it's just like your this is right here, your OS is present here, you have a queue. All the requests, read write requests are coming here, and they will start jumping up in the queue. Jumping up as in they will start getting included in the queue. What your disk will do is it will try to merge most of those commands together, as in which are pointing to a given sector. As in 3 reads came, 3 writes have come up. Maybe 2 reads want to read from the same sector. So they will just jumble this up. Jumble this up and club it together. And so that they can be issued together to that particular sector. So this is the queue. The scheduler there, we have a deadline scheduler, we have a CFQ scheduler, and we have a loop scheduler. So in general, people generally go for deadline or CFQ for your hard disk and loop for your SSD. Because loop is something like first come first serve. Because in SSDs, you don't have to merge anything. That is not going to provide you any kind of optimization. In hard disk, because the disk is rotating, it will play a very important role that you should be clubbing up requests or write requests or read requests which are pointing to the same block. You are optimizing over there. We are running out of time, so I'm not able to cover much. We can just go to the main experiment, like one small experiment that I had thought of. And after that, we'll have to finish. Okay, fine. So let's take a simple example. We have to be very fast in that. We are writing a file. So the file query comes over the network, some bytes are coming over the network, it is going onto the ROM, something is being processed, it is coming onto the disk. Now, if you are trying to read something, from where are we reading? If we are trying to read the file, from where are we reading? It will be from the ROM and not the disk, because space has there, and most of the data will be written from the disk. Sorry, the ROM. It will not be the file disk. With the same example, I want to increase double my throughput. What should I do? I cannot add nodes. What should I do here? Repeat this, Agatha.
That's it.
Wrong. That is very expensive. What I can do is I can add one more disk and I can split my files into two parts. So that one of the files is present in disk 1, other file is present in the disk 2. Now when I am reading manually, I can just speed up the whole process. So these are very simple tuning things that you can leverage to like increase the throughput to max. I'll hand over to Jagdish. I'm really sorry. I can look at the time and I'm really sorry.
That's good.
Okay. So, when doing a benchmark, there are actually three things which we may have to concentrate. One, a bottleneck there can be there in the client side, or in the network, or in the server side. Again, as Kunal mentioned, in server side there can be 4 resources where you can end up bottleneck. So let's see how we should make the setup for the clients to do the benchmark. Make sure that none of your client threads are having the logs so that they can independently hit the server, thereby getting the maximum throughput and actually doing the benchmark of the server rather than the client. And please don't do MRs for doing benchmarks. We ended up with having a lot of debate over that. MR itself has some restrictions, and on top of that, your line code will also have more restrictions on it. Thereby, not continuously hitting the server at the desired rate. Okay, and on the so once on one incident when we tried to do benchmark, we didn't observe the client side, and actually that was what was bottlenecking our whole experiment, and ended up getting the wrong results. So in case you want to simulate having multiple, if you feel that the network is actually being bottlenecked, so try to run it on the multiple machines so that the network will be uniformly distributed, network bandwidth will be uniformly distributed. And again, so this is something which we learned from doing benchmark from the AWS clusters. By theory, if you use AWS, you need to say that you are using the shared resource, which means that whatever they are promising may not be actually what you are actually getting. So, and also from the experiments, AWS suffers from a lot of network glitches, which means you will always have the connection getting cut frequently. So whenever you start doing some benchmarking for a particular data store, say for instance, Cassandra or Aerospike for example, know the architecture and your use case properly. For example, your use case would be write continuously and read only once and day or something like that for analytics purpose. So probably the data store may claim that the QPS given by them is 40K QPS, but your use case may not be the same, because every data store has its own architecture meant for a separate use case. For instance, you can go to the Cassandra, it's always write and read later only once. The read to write ratio will be x is to 1. Sorry, 1 is to x. To start with the benchmark, start with the theoretical limitation. To start with, you will know the throughput offered by your hard disk and the throughput offered by your network bandwidth. So from that you can actually do a reverse calculation and get to know that you can expect a QPS of say xk QPS, and then try to start with the benchmark and try to connect the dots whether this matches with your actual experiments or not. Decide upon the machine configuration, which means that so when when you are going to actually do the benchmark, try to simulate as much as your production environment. Assume that your requirement of the production environment is 100K QPS with 10 nodes. If you are only provided with 4 nodes, try to generate 40K QPS if it is possible or not. Use the applications as per the best practices of store. So every store recommends their own best practices. Say the SSD tuning parameters may be one such example. Similarly, they want to have their RAM dedicated as so many GBs and etc. So just tune it before you start benchmark. And they themselves come with their own benchmarking tool supporting their cost. So just run the benchmarks and then see, verify whether you have the right setup for the benchmark to start with. And write your own client base. Don't depend upon YCSB or something else. They have their own use case implemented in YCSB, and that may not be the same as you actually want. While running the benchmark tools, use the monitored commands which Gunnar have mentioned to make sure that you are not bottlenecking any of those resources. And once you have done the benchmark, try to connect the dots whether you are making sense or not. See, if you are not bottlenecking anywhere, try to reason out why you couldn't bottleneck anywhere. So it is never possible that you are not bottlenecking any of the resources and you are coming up with some QPS which is shown. If possible, try to tune the resources. We ended up tuning the kernel resources for Cassandra and we actually found a significant improvement there. Once you have done the experiments, repeat it many times to see whether you are getting the same results again. And finally, once you are satisfied with the results, try to have a long running test just to make sure that your application is not breaking because of JCs or the application is not giving reset QPS because of compaction running in the backend. And again, so this is something very basic. So you have a number of concurrent users versus the throughput given. So when you start increase the number of threads at the client side, so you will start seeing the increased throughput, and this would be the third. After some time, it will have a steady state, which is what is given to the server. But once you have reached the bucket zone, it will start dropping because the server is being overloaded there. So all you have to do is find the sweet spot between the heavy load zone, which is B should be your ideal point in production. Well, the mistakes which we had and what we found other people are having while doing benchmarks. Standard tools can be misleading, just as you told YCSB, you can't rely on them because they have their own use case and they only support so much read and write patterns which they support, and your this case may be totally different. Network connectivity is the main bottleneck in most cases, and we often tend to ignore looking at the stats only at the server side. Client itself can go for a GC which we observed by running with our benchmarking using MapReduce. Wrong size of data. So just as I mentioned, all the YCSB benchmarks have very less payload of say in terms of bytes, but actually your use case could be writing some 100 KB byte every time. So choose the correct size of data and customize it by running it in your custom experiments. Choosing wrong compaction strategy. So again, depending upon the use case, one may have to come up with the right compaction strategy because most of the open source projects have multiple layers of compaction, saying that they want to satisfy everyone. If you end up with having a wrong compaction policy when you are running a wrong running test, you will end up having a server failure or something like that. They are not being not available for you. Choosing wrong sets of questions on AWS. So as I told before, when you are choosing AWS, it comes with a clause saying that you share the resource. When you go for a higher run machine, the chance of sharing the machines comes down. Thereby, you can can safely assume that you will be the only one using that resource. Again, as mentioned, don't use the MR clients. And the latency calculation, you can have two different perspectives. These metrics published by the server or the latency is only answer with the perspective of the server. But when you are writing the client code, make sure that you have the latencies mentioned there, because that is the only one which you will observe in production. Logical analysis should be done after every benchmarking and try to connect the dots, where you are actually making the resources fully utilized and not where you are not fully utilizing. And then JVM tuning should be done, and it is not often done. It can lead to your awesome results later. And then if there are any questions, Kunal will be able to answer.
So have you guys automated any of this stuff in terms of running multiple times and collecting?
We have written script so many times that we have our custom setup and it is being used in the.
What were the databases? What were the databases that you're benchmarking for the key values?
We actually tried a HBase, Cassandra, and Aerospec. At least for our use case, that's what the architecture that's where the architecture makes sense to us.
I have a question. One of your recommendation was don't use specific clients and use high-level clients, right? What are your ratings for recommending that? What are the corner case scenarios you have seen with specific clients?
Fine, so the default settings on the ICSSD. So we can say the payload rate there is how much? 20 bytes. While doing benchmarking, general latency would be how much? I want to push 20 million records. That's it. So 20 million into 20 bytes. That is how much? 200 MB. That is just going to decide in the page cache. When you read it back, you are just measuring how much, what is the speed of your ROM. Who wants to measure the speed of the RAM? I want the speed. Why is it going to disk and coming back? What is my speed? How is my store loading in that case? So those are the problems with ICSSD. So you have to really go and figure out in their context what is the payload, what is happening at the runtime, how much payload they are offering, and is that even correlating to our prod machines? Will our prod machine have so much of RAM that everything can be held in the page cache? If yes, it's good. If not, then you have to make your best plans.
And another question is, what is your competition strategy when you are measuring HBase and Cassandra?
See, we have a different use case. So for our use case, level tier is what we wanted, because we want to read very fast. So it was level tier because it can be split across this. Just say, for example, the size tier of action policy and etc. All the data will be pumped and like compacted and saved into one disk. So when you try to read that, it will be obviously slow, because it's a multi-thread application. All of them wanting to go and read from the same disk, as compared to if the file system is split across multiple disks and the threads now reading from multiple disks. So you are supposed much more in that case.
So can you publish your benchmark results?
See, the slide, the first result said that it depends upon your use case. I can say for my use case, Cassandra is doing the best. You will come up, oh, Cassandra is doing best for me also. Now you go to the part home. So I'm done. I think something wrong.
Yeah, but what are use case? You could mention use case and publish the results.
Sure, like, as in you want publishing right now or?
No, whenever.
Thanks everyone. I think it's been a great discussion. I know we got late by half an hour. So thanks to all the participants and special thanks to all the to the team, the team, and